let us start. So welcome everybody. We are very happy to have Joan here, who is going to talk about this allowable complex matrix in quantum cosmology. Jean-Luc Lehners is a leading expert on any issues with quantum gravity and quantum cosmology. Currently, he is a professor at Max-Planck-Institute and Albert-Einstein-Institute in Gom, Germany. So Joan, we can start. Thank you.
Thanks very much for the invitation to give this talk. Yes, as the title says, I want to get to the topic of complex metrics in quantum cosmology. However, I should say that I will first start with sort of a more general overview of recent progress in quantum cosmology, because this serves as I think, necessary or useful background to better understand the issue of complex metrics. And also let me say that I have on the current projects that I'm working on, I have two collaborators, my student Caroline Jonas and postdoc Jérôme Quintin. So if I'm not mentioning them explicitly, nevertheless, they are involved in all the recent results that I will mention. Now, why should we be interested in gravitational path integrals? Well, in some sense, this is the simplest way of combining gravity and quantum theory. The Feynman's path integral approach to quantum mechanics is essentially the most useful formulation of quantum theory in terms of just generalizing it to more and more complicated systems, and including also gravity. And so even though it's fairly clear that this will not be the ultimate theory of quantum gravity, certainly it is likely to be a useful theory at the semi-classical level. And so it should already provide us with insights of what happens when gravity and quantum theory are combined. But there's an immediate question that also comes up when you do this, and this is the question of what should you actually sum over? I mean, in this sum over histories or sum over paths, what should the paths be? You know, should you sum over, it's clear one should sum over geometries, but over which geometries? And this is the question that will sort of be the guiding question as we go along. Now, let me start first with a bit of a review of the no boundary proposal, because this is to some extent the best understood proposal for what one should sum over. And so it is useful to analyze this in some detail. And one can motivate the no boundary proposal in the following way. If you imagine that our universe is a circle where we suppress other dimensions, then, you know, as we go to the past, this circle was smaller and smaller because the universe was smaller. And wherever, no matter how far back you go, where this early surface to which you extrapolate back, you will have to specify some boundary conditions there. And you can always ask what happened before that. And so you get a kind of an infinite regression. However, every time you discover an earlier phase of cosmology, you will again ask what happened before. And the no boundary proposal is a way of stopping this infinite regression. The idea is that the geometry of the universe that one should sum over should be rounded off in the past, so as to have no boundary. If there is no boundary, then there is nothing else before. And so in a sense, this is then a replacement of the Big Bang. And moreover, it immediately, as this rounding off also immediately implies that curvatures don't blow up. So everything should be calculable. That's the big advantage, because if there is no singularity, then one should be able to just calculate everything explicitly. Now, these ideas were written down and explained in detail by Hartle and Hawking in their famous paper from 1983, based on some earlier, more sort of conceptual papers by Hawking. And the way they define this integral, this path integral for gravity, is to say that the wave function of the universe should be calculated by summing over compact, regular Euclidean metrics. This was their proposal, right? Then the question is, what does it mean and what does it imply? But this is the proposal as it was originally written down. Now, these metrics, I should say, these should have, of course, one boundary, which you can think of as the current spatial slice of the universe. So there must be one boundary, so some final conditions, which could be just, for instance, the current Hubble rate or the current matter content of the universe, or it could be just the current size of the universe, something like that. But then in summing over metrics, one should sum over all metrics which have this as their only boundary and no other boundary. Now, from this definition, there were some immediate expectations. The first is that the wave function should be real, because if it is defined as a sum over purely real Euclidean metrics, there is nothing complex involved in this sum. So the wave function itself then should be real. Also, it was hoped that this was a unique definition of the wave function. Moreover, with an analogy with how you calculate the ground state in quantum field theory, the idea was also that by summing over Euclidean metrics, you would get the ground state, an expression for the ground state of the universe. And then the other points were that this is a true, the no boundary wave function is supposed to be a true theory of initial conditions, meaning that it will provide probabilities for different histories of the universe, or if you like, probabilities for different initial conditions. And moreover, because this was formulated in Euclidean geometry, one reason for formulating this in Euclidean geometry was that it was hoped that this would allow one to include topology change. Because if you have Euclidean metrics, it's easy to include non-trivial topologies where the universe changes from, say, here a sphere to a point and then to another geometry. Now, it should be said that from the beginning, there were a number of puzzles with this proposal. Let me just mention 3 puzzles. The first is that there is a kind of a conflict with the uncertainty principle. You can see this by looking at the Friedmann equation. I've written the Friedmann equation here by multiplying by the scale factor squared, and assuming that the universe has closed spatial sections with positive curvature. Now, if you say that you want to sum over compact metrics, this means that at the origin of the universe, where the universe is nucleates, A should be 0. But now at the same time, you want everything to be calculable. There should be no singularity there. So, but if there is no singularity, that means that the Friedmann equation must remain regular. And the condition for this is that A dot must be equal to plus or minus I. Or in other words, the derivative of A in the Euclidean time direction should be plus or minus 1. But you see, you cannot fix both A and A dot, because that's in conflict with the uncertainty principle. And so when you try to implement the no boundary proposal, you must choose. Do you want to put a condition on A or a condition on A dot? But you certainly cannot impose conditions on both. So as it was initially formulated, the sum of our compact regular metrics seems to be impossible to implement. Another problem is a general problem of gravity. That's the conformal mode problem. And this is that if you look at the action.
May I ask a question here, or should I ask it again?
Sure.
Yeah.
No,
so
please.
Yeah, in the previous slide, so when you say of fixing A as well as A dot, and so to have uncertainty, you have to have this A and A dot as some kind of a symplectic dual. So what is the kind of symplectic structure here for Friedmann's?
I simply mean that if you look at the action, then the momentum canonically conjugate to A is A dot. Or is so some combination of A and A dot.
Description and put it in the Einstein action, Einstein-Hilbert action.
It would just be, yes. So if you rewrite the action as sort of a phase space action,
and so there will be symplectic dual of each other.
They will be, yes, they will be conjugate variables. Yes.
Okay, thank you.
Okay, Jean, I have a question if I can ask.
Sure.
Yeah, point is there is a lapse involved. So you are assuming one is momenta, probably the A dot. It's related to the momenta, and A is the coordinate. But then what about the lapse? Unless you fix it, they are not coordinate and momentum, and there is no conflict with quantum
Yeah,
mechanics.
that's right.
There is no, well, the lapse has no momentum, right? It's a separate variable.
Yeah, I'm saying that A and A dots are coordinate and momentum only
Yes.
through the n, the lapse.
Yes,
Unless
the full relationship involves the lapse also. So you will have
right. So
A dot will
unless
always
you-
appear in the combination A dot divided by n by the lapse.
Right. So unless you fix n, you can't say one is coordinate and the other is momentum. And if you can't say that, there is no conflict through uncertainty principle.
That's basically what I was asking. Yeah.
So okay, so if I wrote, all right, then I should have written this equation out in more detail. That really this term would have been A dot squared divided by n squared. And the momentum is related to A dot over n. So really, the condition that you have to impose at A equals 0 is a condition on A dot over n.
Then it's fine. Thanks.
And would be involved in this relation if I wrote it out more properly.
Okay, so you have fixed n in some way here in this equation. Okay.
Well, A dot over n would have to be fixed.
Right.
And that is essentially the momentum conjugate to A. So either way, that you have so you run into the trouble that you want to fix a field and its conjugate momentum at the same time.
Right. Okay. Thanks.
Thank you.
Welcome. Yeah. No, that's right. I should have done this more properly. I went a bit fast here. So here I have the lapse now. Let's see. So what I want to say is, yes, so the conformal mode problem is a general problem for gravity, for quantizing gravity. And you see this by looking at the action for gravity and matter fields. So if you look at the kinetic terms, the kinetic term for the scale factor has the opposite sign to the kinetic terms for any matter fields. Here it would be, for instance, a scalar field phi. But it's true for all other matter fields, and in fact also true for other deformations of the metric. So if you have anisotropies, they also have a kinetic term that is the opposite of the kinetic term for the scale factor. Now, that means that when you now write the path integral over this action, this integrand will be unbounded both above and below. And so it's not clear how one should define such an integral. Furthermore, when Halliwell and Luco tried to look at specific mini-superspace models, where you have imposed symmetry simplifications, then they found that actually it was not so clear that this definition of the no-boundary proposal was actually unique. This was an open question for quite some time. Actually, it still is to some extent an open question. Now, I have to say that faced with these sort of potential problems or puzzles, the thing that people did was just a pragmatic approach, which was to focus on the saddle points of the path integral. So the path integral is dominated by saddle points, and these saddle points are actually solutions of the classical equations of motion. The only thing is that they can be complex solutions of the classical equations of motion, and in fact the no boundary conditions force them to be complex solutions in general. Now, the advantage of just looking at the saddle points is that now you can fix both the field values and the momenta, because these are just classical solutions. Moreover, you don't need to worry about the conformal mode problem because you're not actually doing the summing in the path integral. And so also uniqueness is not really a problem because you're not looking at the contours of integration. So you kind of just simply ignore or get around the problems that I mentioned by looking at the saddle points only. Nevertheless, this already is non-trivial because the question then is, do saddle points exist that have the required properties, and do they give something which could provide a realistic cosmology? And in fact, these results that were found in the early 80s and 90s confirmed that such saddle points in fact exist. They have a shape which is always, roughly speaking, half of a full sphere at the bottom. The point at the bottom is usually called the south pole of the solution. And then this is joined to a portion or half of the de Sitter hyperboloid in the future. If you add a scalar field, the geometry is more complex, and in fact, the geometry and the scalar field both take complex values. Also, then you don't have this gluing of a Euclidean to a Lorentzian solution. Rather, you have an approximately Euclidean part and an approximately Lorentzian part. But in fact, the geometry and the scalar field are in general everywhere complex. I'm showing this with these graphs here. And this is an example. You should think of these graphs as just describing the saddle point geometry, and which interpolates between the South Pole at 0 here and this final point, this green point, which is which is in fact representing the final three-dimensional spatial surface. Now you could take any path from the South Pole to this final point, and this would be a potential solution. This would be a solution of the equations of motion. The typical, because this is the complexified time plane, the typical way that the solution is normally represented is by going in the Euclidean direction first, which is the horizontal line here, and then in the Lorentzian direction, which would be in the vertical direction next. But you are free to deform this path any way you like. As long as there are no singularities, Cauchy's theorem allows you to deform this path any way you like. The dark line is the line where the scalar field takes real values, and in this right graph, the dark line is the line where the scalar field takes real values. Sorry, left for the scale factor, right for the scalar field. And so you see that, in fact, at late times, in the Lorentzian direction, the fields and the geometry become real or approximately real. And in this sense, the no-boundary proposal then sort of predicts the emergence of a classical space-time. But at early times, if you like, this, maybe I should not say times because this is now a complexified time, but close to the South Pole, everything is complex. Then, in order to actually describe how the universe evolves, one would calculate a sequence of such wave functions with different final conditions. So that, with final conditions where the universe gets larger and larger, for instance. And then if the wave function, as you vary these final conditions, is of WKB form, meaning that it has a very fast varying phase and a very slowly varying amplitude A, then then you have a semi-classical wave function which actually describes an approximately classical universe. And in this way, you actually predict, that certain histories describe classical universes. Because it is not, with a wave function in general, it is not guaranteed that the universe will be classical at all. Moreover, if you have such a slowly varying or basically constant amplitude, you see then also you can assign a probability, or at least a relative probability, to a particular history. Because then mod psi squared, which is then A squared, is constant, and is constant along this entire history of the universe. So this is a way of giving probabilities to different evolutions of the universe. Now, you can ask, does this happen automatically, that the wave function ends up being of this WKB form? And in fact, that's not true. And this is one of the interesting aspects. Is that you seem to need an attractor mechanism for the wave function to reach this WKB form. Inflation is such an example. In fact, it's the best known example. If you calculate the wave function for the no boundary wave function for inflation, what you find is that the amplitude goes as e to the 1 over the v of phi, where phi is the South Pole value of the scalar field. And so is it basically constant, or is constant to first approximation, plus a phase which goes in proportion to the volume of the universe. So you see that, in fact, indeed, as the universe grows, the phase varies more and more rapidly, and the amplitude is approximately constant. So you get a probability for different histories of the universe. And you see, actually, if you start at lower values of the potential, this is preferred. This gives you a higher probability. this is one, well, the question is whether this is an advantage or a disadvantage is has been debated for a long time. I will come back to this later on, but really it means that you prefer to be low on the potential. It turns out there's a second mechanism which also works, that's ekparosis, which is a phase of slow contraction. So it turns out that you can find no boundary solutions which immediately go over into a phase of slow contraction. So this is a bit funny because you think of creating the universe from nothing, you would think the universe would have to expand, but that's not true. It turns out that you can create the universe from nothing and immediately the geometry becomes very large and starts contracting. And in fact, in this case, you also find that the wave function reaches this WKB form and that you predict a classical spacetime. And these are the only two possibilities that are currently known, which drive the wave function to this WKB form. However, for the ekparotic case, you have the basic puzzle that you have in all bouncing models, which is to understand how you go from the contracting phase to the expanding phase. And this is still not completely understood at present. So one needs to always have something like a violation of the null energy condition, and it's not clear that this is compatible with quantum theory. So at the moment, these instantons are, it's not clear that the bounce phase is really realistic. Now, okay, so let me just recap briefly what these early works achieved. So they showed that the wave function indeed can explain why there are classical realms where the universe is classical, but only if the potential allows either for inflation or ekparosis. As I said, low values of the potential are preferred, and this typically means that short inflationary phases are preferred over longer ones, but in the ekparotic case, it means the opposite. Longer ekparotic phases are preferred. Then if you look at probabilities, you have to, so people then essentially try to combine this with anthropic arguments to argue that you need a long inflationary phase, otherwise the universe would simply not have enough, would not become large enough and would not have enough structure. Now, these arguments I think are a bit premature, but as I said, I will come back later to the issue of probabilities. There's another nice feature of the no boundary case, which you see when you start adding perturbations. So if you add perturbations, for instance, here, gravitational wave perturbations, little h, you can solve now on this no boundary background geometry. And it turns out that there are two solutions. One is regular, as at a equals 0, so where the instanton shrinks to 0 size. There is one regular solution and another one which becomes infinite there. So you are forced to choose the regular solution. And the nice thing is that this regular solution is the Bunch-Davies vacuum for these perturbations. So you automatically get, as a byproduct of the no boundary wave function, an explanation for why the perturbation started in the Bunch-Davies state. You don't need sort of a separate explanation for this. There is a subtlety, however, with the perturbations, and this plays a big role later on. Now, the thing is that if you think of the no boundary geometries as combining a Lorentzian geometry with a Euclidean geometry, there are two ways of gluing a Euclidean geometry, because there are two directions in which you could do the Wick rotation from Lorentzian to Euclidean time. And if you do it as Hartle and Hawking have proposed, you get a wave function which has a probability which goes as e to the 1 over the vacuum energy, lambda. If you do the opposite Wick rotation, which is what is typically done in the tunneling proposal of Vilenkin, you get a probability which goes as e to the minus 1 over lambda. So in the Hartle-Hawking case, you prefer low values of the potential. In the Vilenkin case, you prefer high values of the potential. But for the perturbations, this makes an important difference, because in the Hartle-Hawking case, the perturbations are suppressed. They're basically probability for perturbations is a Gaussian distribution. And so these are stable universes. But in the other case, in the tunneling case, the tensor perturbations have an inverse Gaussian distribution. It goes as e to the plus h squared. And so these perturbations are unstable, meaning that larger perturbations are more likely. And then the whole, so you do not predict to be, to have a nearly smooth universe on large scales, but rather you would predict the universe to be extremely lumpy. And in fact, the calculation breaks down because the stronger these perturbations are, the more likely they are. And so the most likely perturbations would be such that the universe immediately recollapses. So now, after this, let's get to some more recent developments. The question is now, can we maybe understand the issues that I was discussing at the beginning? Can we understand these issues about the conformal mode problem and about uniqueness of the no boundary wave function, and also about just what integration contours one should sum over, which metrics should really be summed over. Now, for this, again, it is easiest to start, or the only way to do it at the moment is to do it in mini-superspace models, where you already choose an ansatz for the metric of the universe and an ansatz which has certain symmetry simplifications. In particular, so we will choose, I will start here with a case where the universe is considered to be spatially isotropic and homogeneous. So the spatial sections are 3 spheres. There's a scale factor squared, q. Normally this would be a squared, but a squared is now written as q. And there's a time part to the metric. Now this, it is useful to do this particular rescaling of the time component of the metric. So normally one would just have minus n squared dt squared, but it is very useful to rescale this by a factor of 1 over q, because it makes the action extremely simple. It means that the action for gravity plus cosmological constant lambda becomes quadratic in q. There's a kinetic term for q, and then there's a potential, which is basically linear in q. There's a constant term from the curvature of the 3-sphere, and then there's this linear term from the cosmological constant. So the action for gravity and cosmological constant becomes extremely simple, and one can then, to a large extent, do the path integral analytically. The question now is, how do we, in practice, how do we actually implement the no boundary proposal? As I said at the beginning, the idea was that it should be defined as a sum over compact, regular Euclidean metrics. Now, it seems impossible to impose compactness and regularity together, hence we should try something. And it was always considered that compactness was the most important condition. So really we should start by sum over metrics that start at 0 size. Now this can be done. And in fact, the integral over this scale factor q can be done exactly because the action was quadratic in q. So that integral reduces to a Gaussian integral and can just be done. And then what we're left with is just an integral over the lapse function n. That integral of the lapse function is a bit complicated. So it is this integral here. The integrand contains an n cubed term, an n term, and a 1 over n term. Q1 here is the final size of the universe. So this is what we impose, that the final size of the universe is Q1. And we start from 0 size. So we can actually analyze this integral using steepest descent methods, or if you do this in a more fancy way, it's called Picard-Lefschetz theory. But actually, for our purposes, really, it is essentially just we will just do a saddle point approximation. In fact, Picard-Lefschetz theory is sort of the more precise mathematical theory for doing a systematic saddle point approximation. So it tells you exactly how to do the saddle point approximation. Because there's a cubic term and a 1 over n term, so if you look at saddle points, there will be 4 saddle points. The equation for saddle points is a 4th order equation. There are 4 solutions, which are all 4 complex. And now we should look at the steepest descent paths that emanate from these saddle points.
Hi, Jia. This is Sandeepan.
Yes.
Can I ask a questioning?
Yes, please.
Yeah. So this is like you are starting from 0 size, but in the Lorentzian signature, right? Which is maybe scale factor is 0.
Actually, I'm not saying anything about the signature at this point. The metric is written with this minus sign. So
right.
That means if n is real, then this is Lorentzian signature. If n is complex, then this is Euclidean signature.
Okay, but you are not considering the boundary term in the action, is it so?
In
The
fact,
curvature term,
because
because
the Gibbons-Hawking-York term, this is included. So if you want to fix the size of the universe, this is a Dirichlet condition, and you have to include the Gibbons-Hawking-York term.
Right. Okay.
Now it turns out that, so this is in particular important for the final boundary, because we want the scale factor to reach this value Q1 at the final boundary. Okay. It turns out that when you start from 0 size, then in fact this Gibbons-Hawking-York term at 0 size is also 0.
I see. Okay.
So we do include it, but in fact it ends up being 0. So if we had forgotten about it, it would not have made a difference.
Right. Right. Okay. That's what I wanted to confirm. Thank you.
But yes, but it should be included. And in fact, for instance, if you want to do this calculation and you say you go from a small scale factor, not 0, but just some small non-zero scale factor to a large one, then you certainly need to include it.
Then you have to include it, yes.
And then you can take the limit where you let the scale factor go to 0, and then everything will work out fine. If you don't include it, for instance, this limit would not work.
Also, another possibility is, suppose you change your boundary condition, then even for 0 universe size, if you don't rule that out, then even then the Gibbons-Hawking can have contributions. But that is not.
But not for this metric.
Right. Right. Okay.
But it can in general. That's right.
Right. Thank you.
Yes. Yes. So one should certainly include it. If you want to impose a Dirichlet condition, you must include it, I would say. And then if it happens to be 0, well, then so be it. But in order to do it properly, you should include it. And this is the result that one gets, and this is, by including this term, because in fact it is important at the final boundary. Now, you see, I have not said anything about the lapse integral yet, what contour of integration we should use for the lapse. I just wrote this as an integral over lapse, and we haven't said yet what values of the lapse we actually want to integrate over. And so it's already interesting that the saddle points come out to be at complex values of the lapse, where already you know that then the metric is neither Lorentzian nor Euclidean. So here, what I'm showing you here is basically now in the complexified plane of the lapse. So this is the plane of the lapse function along. So the horizontal line here is the real axis for the lapse. So the lapse takes real values along this horizontal line. The vertical line are pure imaginary values of the lapse. So roughly correspond to Euclidean universes. And you see the saddle points are these 4 orange points, which are at complex values. Now, the black lines are the steepest ascent and descent lines. So where the magnitude of the integrand is getting larger or smaller. And the arrows always show a downwards flow. So the arrows show you the direction in which the magnitude of the integrand gets smaller. And then if we want to have a convergent integral, we need to integrate over steepest descent contours, because then, away from the saddle point, the integral gets less and less contributions and it will be convergent. If we want to integrate over real values of the lapse as a defining contour, you see, this is in fact not clear that this is a convergent integral, because the integral is an integral over e to the I times some function of n. And you see then at large n, this integral oscillates very rapidly. And it's not, but it has modulus 1 everywhere. So it is only conditionally convergent. It is not absolutely convergent. What I indicated with colors here is asymptotically, if there is a green region, this means that the integral is convergent. If there is a red region, it means it is divergent. And yellow is in between. So if we integrate along real values, we are in between because we are just in this region of conditional convergence. But if you can deform this contour using Cauchy's theorem to this dashed orange line, which follows the steepest descent contour along this around this saddle point number 1. And so the integral can be deformed, even if we define it originally to be over real values of n, it can be deformed to run over these complex values, and then that is the relevant saddle point. In fact, to be really clear about this, one can verify. So Picard-Lefschetz theory instructs you to do this, and you can verify that the arcs near 0 and arc at infinity, to get back to the original contour, they give 0 contribution. So this is really this deformation does not change the result. Now I should immediately point out that, you see, if you wanted to sum over Euclidean metrics as was originally proposed, this doesn't work, because either in the upper half plane you go into a region of divergence at infinity, or in the lower half plane you have a region of divergence near 0. So whichever way you do it, this sum over Euclidean metrics just doesn't exist. Now there's another issue, which is that the saddle points in the upper half plane are unstable. They have these unstable fluctuations, and the saddle points in the lower half plane have stable fluctuations. So let me say it maybe in a different way, that wherever this saddle point is located determines how you are forced to do the Wick rotation, or it tells you how the Wick rotation is chosen, the direction of the Wick rotation. So what we find is that if you define the integral as a sum over Lorentzian metrics, it picks out an unstable saddle point. And the problem is that if you actually wanted to sum over stable saddle points, you can find some other contour that includes stable saddle point. You see the steepest descent path from the stable saddle point runs directly to the unstable saddle point. So if you get the stable one, you will also get the unstable one included. And so the instabilities will still be there. So this doesn't seem to work very well. There has been a lot of debate about this. I refer you to papers by the authors listed below if you're interested. But what I want to do is I want to do something else now, which is to focus on the regularity condition rather than compactness. So the initial proposal was to say sum over compact and regular and Euclidean metrics. Compact and Euclidean does not seem to work, but you can ask, what about regular? Does that work? So we would try to impose rather that the initial momentum is fixed. So q dot over 2n is fixed to be I. This is the condition, as I showed earlier from the Friedmann equation. This is the condition that the metrics are regular. Now,
I'm sorry, what do you mean by regular exactly?
I mean that the Friedmann equation, the constraint equation, will be satisfied and will not go. There will be no term there that goes to infinity.
Okay.
So there's no singularity.
Thanks.
This avoids singularity. And you see, there is an immediate advantage to this, which is that this q dot, this sort of the initial direction of the scale factor, in the direction in which it starts expanding, you could have chosen a different sign. You could choose I or minus I. Both would give regularity, but this choice of sign is also the choice of Wick rotation, because it tells you now in which direction the time direction should be rotated. And so if you impose regularity, you fix the Wick rotation. And so you can fix this sign such that you get stable metrics. And in fact, when you now look when you now perform the same steps as I did before, there are only 2 saddle points, and there are just these saddle points in the lower half plane. So you're left with just these two stable saddle points. Moreover, now you see the contour along the real line is asymptotically in these green regions, so it is convergent. So you can sum over Lorentzian metrics, and get a convergent integral. And moreover, that contour can be deformed to sum over the 2. But you see, you also sum over geometries that are regular in the interior. And so if you impose this in the path integral, you need to impose the exact same condition. Again, this q dot over 2n equals I. It's the same condition that you need to impose when you do the anti-de Sitter path integral than if you do the de Sitter one. So there is a direct correspondence at the level of at the simple level here of having a pure cosmological constant. There's a direct correspondence between de Sitter no boundary integrals and anti-de Sitter path integrals. In fact, if in the anti-de Sitter integrals you include black holes, you are forced to choose this regularity condition. This is something that my former student Alice Ditucci and Michal Heller and I showed a couple of years ago. And so the advantage is that, for the ADS path integral, you also have a CFT dual, and you know what the CFT result should be. And so you kind of have a check that what you're doing is correct. And so it turns out that ADS CFT implies that the wave function is given by this Airy function, in this case, an Airy B function. And because of this correspondence between anti-de Sitter and de Sitter, you see you can now simply analytically continue this result. You let the cosmological constant go from negative to positive values, and then you immediately find the no boundary wave function, which is an Airy function. So this is pretty nice because you have then a sequence of checks from the CFT to ADS to DS, and the whole thing fits together. So I think this gives a good justification or support for this proposal that one should impose a regularity condition. There are, let me just mention 2 consequences that come out of this correspondence between ADS and DS. If you have ADS, you have 2 possible saddle points, but only one ends up being relevant. You can either have a universe which starts at 0 size and then grows, or you can have a universe which already starts as a sphere, and then there's a new kind of separate part of the universe that gets glued onto it and that grows. So basically you have a saddle point which has sort of the trivial topology, and you have a saddle point which has this non-trivial topology where you have an extra sphere glued on. And from the path integral and from the comparison with the CFT result, one finds immediately that only this topologically simple contribution is relevant. So there is no extra contribution from these topologically non-trivial space-times. So even though there could have been, in principle, the formalism would have allowed it, there isn't. In the de Sitter case, the situation is a bit different. So again, the universe starts from 0 size, and there is just sort of one Euclidean geometry that grows. But then when the universe reaches a certain size, this one saddle point splits into 2 saddle points, which are now like time reversed universes. This is necessary because the wave function was real. So you always get sort of one universe and then its complex conjugate added to it. And this splitting of the saddle point from 1 saddle point to 2 saddle points is known as a Stokes phenomenon. And in a sense, that's the moment at which time starts showing up. So before that, it was a purely Euclidean, purely spatial geometry. And then it turns into a geometry which now includes a time direction. So time emerges as a direct consequence of this Stokes phenomenon, if you want to see it from a mathematical point of view. Okay, let me say one more thing quickly about this, and then we move on to the issue of complex metrics in general. And this is that this regularity condition is a condition on the momentum, and it can be, if you look at the Wheeler-DeWitt equation and you try and see what this regularity condition translates into, then it's pretty interesting. It turns out that the Wheeler-DeWitt equation, I will not go into the details, but the Wheeler-DeWitt equation reduces to a single term, which is saying that d psi by dp is 0. So this regularity condition is also the condition that there is no momentum transfer at the nucleation of the universe. Intuitively, this makes sense. This means really that there is nothing that flows into the universe when it is created. In other words, the universe is really self-contained. And, you know, because we are now imposing a regularity condition, this is like working in momentum space. But you see, if we work in momentum space, then I d by dp is nothing else than the operator version of q, of q. So it's q hat. It's basically the operator version of the scale factor of the universe acting on the wave function. And then saying that there is no momentum transfer is the same as saying that the initial size of the universe is 0, except that you are saying it in its Fourier transformed version in momentum space. So this means that there actually is a way of defining the no-boundary wave function directly at the level of the Wheeler-DeWitt equation. Yes, please.
This is Sudipto. So maybe a very stupid question, but in general, the no-boundary wave function need not be a solution of the Wheeler-DeWitt equation. Is that correct?
No, it is. It is. So yes, by construction, if the path integral provides you with solutions of the Wheeler-DeWitt equation. One can show this quite generally.
Okay.
The issue is that it's very hard to impose boundary conditions for the Wheeler-DeWitt equation.
Yes. Indeed.
Whereas in the path integral, it's very easy.
Okay. I see.
And so the trouble normally is that the Wheeler-DeWitt equation has an infinite number of solutions, and you don't know which one to pick. But if you work with a path integral, because you can directly fix the boundary conditions, this gives you immediately a unique solution.
Okay. Thanks. Okay.
And that's what I'm saying here is that now if you go back to the Wheeler-DeWitt equation, in fact, it turns out that now you can impose a no boundary condition also on the Wheeler-DeWitt equation. So you impose the Wheeler-DeWitt equation, and in addition, you impose this condition, which I would say is the Wheeler-DeWitt analog of the no boundary condition, which is that there is no momentum flow as the universe is created.
And then the solution space is unique.
And then it collapses the solution space.
Okay.
I have not checked in general if there would be other solutions that would be possible. So I don't know if it is really unique, but it certainly drastically reduces the number of possibilities.
Okay, thanks.
Okay, so this was all done in minisuperspace. Of course, it will be important at some point in the future to extend this to more general metrics. And then also, I did this for pure GR, but we know that we expect, correction terms to come from string theory. And so let me just mention one result, which is that my student Caroline Jonas and we showed that if you include Riemann terms to the nth power, these no boundary solutions are robust. So they are modified, but they are not, they still exist. They have small modifications due to these Riemann terms, but so this looks promising in the sense that it means that these solutions stand a chance of being also solutions of full string theory. Okay, so now let me get to this issue of complex metrics. As we've seen in the path integral, it happens that you need to sum over complex metrics, and moreover, even the saddle points themselves ended up being complex. So the question is really, in general, which complex metrics should be allowed? Should one allow anything or not? Should there be a restriction? There were some early works about this question by Luko and Sorkin, but they looked only at 2 dimensions, so there was not much gravity involved. But they already discussed this question. And then more recently, Kontsevich and Segal made a proposal without gravity again in the context of quantum field theory. And Witten then started extending this criterion to gravity. And I will base my discussion here on a paper that I wrote about this topic 2 or 3 months ago. Now, what Kontsevich and Segal note is that scalars and gauge fields have local covariant stress-energy tensors due to the Weinberg-Witten theorem. And so what you would really want is any quantum field theory to make sense. For quantum field theory to make sense, it should be such that, scalars and gauge fields should have a well-defined action on any background that you choose. So they say they look at quantum field theory in a fixed but curved and potentially complex background. And they say we want the path integral to be able to converge on such a background for any possible scalar field or gauge field configuration. If that's true, then any quantum field theory on these backgrounds is essentially fine. What this means is that you want the integrand to have a magnitude that is smaller than 1. Because if you go bigger than 1, then you will get into a divergence. Because if the fields are real and the metric is real, then the magnitude would be 1, S would be real, and then e to the is would be a pure phase, and then the magnitude would just be, the modulus would just be 1. And if you now integrate over such metrics, then the integral can only converge if the contributions from different configurations has a magnitude that is smaller than 1. But if you now write, so you write the gauge field action, the kinetic term, you see what it means is that the real part of this Euclidean kinetic term must be positive. So the action goes as e to the minus this term. And so if this term is positive, then the magnitude is less than 1, and then the path integral over these fields will converge. Now, you see and this should be true for any P, for any gauge form, because up to the maximum allowed in the dimension that you are in. Because now if this is true for every P, then you can write any quantum field theory on this background and it will be well defined. And so you see this condition involves the determinant of the metric, and it also has these inverse metrics which come from the different field strength. Now, if you write out what this implies for different P's, a useful way of doing this is to note that locally, so at a point, you can always write the metric in diagonal form. You cannot do this globally, typically, but locally you can. And so it's important to realize that this condition that Kontsevich and Segal propose is a local, point-wise criterion. It has to be true at every point in space-time. And so you write the metric in diagonal form. The diagonal entries are these lambda and mu components. And then it turns out this requirement that this is convergent for any P can be rewritten as a very simple condition, namely that the sum of the absolute values of the arguments of these lambdas should be less than pi. This is a slightly, it looks a bit mysterious that this should be the consequence, but if you write out just what these conditions are for different P, you start with 0, P equals 0, 1, 2, 3, and so on, and you combine them, you very quickly see that this is the condition that you get. Essentially, what you find is that you get a sum. Well, let me put it this way. The real part of this expression has to be bigger than 0, meaning that you have to be sort of in only 1/2 of the full complexified plane. And this can be expressed by a condition on the arguments on these lambdas. And if you have to write it out for yourself to see, but it is fairly quick to see in 2 or 3 lines. You would see that you get sums of lambdas with arbitrary or with different prefactors, minus or plus. And then if the sum of the absolute values of these terms is always less than pi, then this criterion will always be satisfied. Now you can ask, what does this mean, this criterion? You see, the metric here is, when we diagonalized it, it was diagonalized with the Kronecker delta. So these lambdas are basically, you can think of as coefficients for a Euclidean metric. So if these metrics are all, if the metric is pure Euclidean, the lambdas would all be real, then the arguments would all be 0, and this sum sigma would be 0. If, however, you have a Lorentzian metric, say simple Minkowski space, then one of the lambdas will be -1, and its argument is pi. And so then the sum of arguments is already pi, meaning you are right at the edge of this inequality. So what this really means is sort of a generalization of Wick rotation, where you say that all metrics are allowed which are complexified such that these gauge fields actions are convergent. And then if you can then you can go to the boundary of the allowed domain, and this is where you will find the Minkowski metrics. So it would mean that we kind of live on the boundary of the domain of allowed metrics. Let me just give very brief justification or partial justification for these assumptions. Now, you see a typical compactification from 4 plus n dimensions would involve a 4-dimensional part, then some gauge fields in the extra dimensions, and also just an internal space, dsn squared. And there would be various scalar fields included. And if you compactify such a theory, you get an effective potential in 4 dimensions, which involves the curvature of the internal dimension, involves scalar fields, and it involves also the gauge fields in the extra dimensions. Now, if you want this theory to make sense in 4 dimensions, then the theory by itself, as it is defined, should involve only real fields. And so this gives justification for parts of the higher dimensional metric to actually be real. So when I was giving this criterion before, one assumption implicit in this was that the field strength for the gauge fields themselves, that they were real. And this gives at least a partial justification for this. Now, when looking at explicit examples of compactifications, it turns out that you do not get the exact same criterion as Kontsevich and Segal if you compare different dimensions, but you get something that is quite close. So I think this is something that is worth pursuing in the future. Well, I should say this is work in progress, so I cannot give a final statement about this yet, but let me say that the conditions one gets are indeed similar to this Kontsevich-Segal criterion and give at least partial support for it. Now, as I just said, yeah, if you go to the Lorentzian metrics, always are exactly at the boundary of this allowable domain. And so really, if you now look at path integrals, it's a bit funny because now, let's say you look at the path integral for the universe to evolve just from today until tomorrow. Then the saddle points are real. They just describe classical expansion of the space-time. And all of the real Lorentzian metrics are on this real n line, the line of real values of the lapse. But you see, this now is the boundary of the allowable domain. Whereas if you go now in the upper half plane or the lower half plane, you are, you go into the interior of the domain of allowable metrics. I have not shown what the full domain of allowable metrics is here. I want to just highlight one point, which is that you see with this classical boundary conditions, this splits the whole space of complex metrics already in 2, because this boundary cannot be crossed. If you now sum over metrics in the path integral, this means that you can only sum over integration contours either in the upper half plane or in the lower half plane, but not integration contours which combine which run across the real end line. And because the saddle points themselves are on this boundary, you see that then the steepest descent contours are cut in half. So you cannot actually define the gravitational path integral over full steepest descent contours, but only up to the saddle points here. This is just the first remark. Now now we can go back to this no boundary case and ask, what does it imply about the integration contours that we had in the no boundary case and about the saddle points themselves, which were complex? Are they allowed or not? And it turns out that actually, if you take the saddle points at face value, as they are given in the metric by the path integral, you see these metrics were always, they had a constant lapse, a constant complex value of the lapse. If I translate this into the sort of standard time coordinate, it means that you go from the initial south pole of the solution to the final point along some curve. But this curve is not like the original proposal that Hawking had of having a Euclidean solution glued onto a Lorentzian solution, but it's something complex in between. And it turns out if you calculate this sum over absolute values of arguments of the metric, this is indeed above, it's this blue line, it is above pi, which is the gray line. So actually these saddle points do not automatically satisfy the Kontsevich-Segal bound. Nevertheless, nothing prevents us from deforming this contour, this time contour. So if we deform it more such that the contour runs more along the Euclidean time direction first, and then more along the Lorentzian time direction, as in this orange curve, then we find that in fact, this Kontsevich-Segal criterion is satisfied. So that means that really we should take the position that that one should treat metrics as equivalent if they can be deformed in such a way. And if one metric out of this equivalence class satisfies the Kontsevich-Segal criterion, then we will take this to be the whole class to be fine. Because let me say that if you deform this time path in this way, you don't change anything about the action, for instance. So you don't change the wave function and you don't change anything else. So you don't change any physical prediction. So it makes sense to consider these as equivalent. Then you can ask, in the space, now away from the saddle point, in the space of the complexified lapse function, which regions are allowed and which regions are not allowed? And there's a surprise in a sense that happens here, which is that there's a very large region in red here, which is not allowed. So again, we have the two saddle points here, these blue dots now. The steepest descent lines are these green solid lines. Steepest ascent are the dashed lines. And in red, I'm showing the region which is not allowed. So where these metrics definitely, they violate this Kontsevich-Segal proposal. What's interesting about this is that the saddle points again lie at the edge of the allowable domain, even though these saddle points are not Lorentzian, but complex. They nevertheless lie right at the edge of the allowable domain. And so again, they cut the integration contours in half. So really, you now have to integrate only over this lower portion of the steepest descent path. And that means that when I said earlier that you had this, you could define the integral over real metrics along this real n line, that's actually not possible anymore. Now, also let me say that, okay, so now if you see, but this contour of integration which you are forced to take, it runs in the negative imaginary direction. It gets closer and closer to the negative imaginary axis. And that's where the Euclidean metrics lie. So really, you get closer and closer to Euclidean metrics. So what you end up with is an integration contour that runs from approximately Euclidean metrics right at the bottom here to more and more Lorentzian metrics until you reach the boundary of the allowable domain. So in a sense, really, this is a compromise between Euclidean and Lorentzian quantum gravity. It combines both. It sums over Euclidean metrics and gets to Lorentzian metrics. But it seems, if you take this criterion seriously, that you can neither have a purely Euclidean integral nor a purely Lorentzian integral. It turns out that if you look at the no boundary proposal in other dimensions, the same thing happens. It's just that the domain of non-allowable metrics gets larger. And in fact, in very high dimensions, like here in 100 dimensions, you see you are left with a very small region that is still allowable, but it has these same characteristics. It goes along the Euclidean axis, and then it goes along parallel to the Lorentzian axis up to the saddle points. So this seems to be quite a general feature, at least when you impose no boundary conditions. Now, oh, I'm already over time. I'm sorry, I did not look at the time. I will try to be brief. Or would you like me to stop at this point?
Maybe take another 5 minutes. Yeah, 5 more minutes. Yeah.
I will try to stick to 5 minutes. Yes, I'm sorry about that. I wasn't paying attention. Let me add one thing, which is that in the no boundary case, what I said earlier was that the saddle points typically involve complex values of the scalar field. Now, if you take this Kontsevich-Segal criterion seriously, then the scalar field should be real. And there is only one exception, and that is when the scalar field sits at an extremum of the potential, either at the maximum or at the minimum. Then it takes on real values. So if you take this seriously, you would restrict to having only, you would restrict, and you would find that actually if you have scalar fields, they have to start at an extremum of the potential. This might be interesting in terms of physical consequences, because you see then the scalar would naturally start at the local maximum. And it would maybe explain why inflation would, after all, have there would be a longer phase of inflation. Now, also, if you have several scalar fields, it would mean that the tendency is for all scalar fields to sit as low as possible on the potential. So if all scalars are at the bottom of the potential, then you just get an empty universe. So one of them, the most likely configuration would be for one of them to be at the local maximum and all the others are at the local minimum. And that might be very interesting for observations, because, like I said, the one which sits at the local maximum would give a longer phase of inflation. And the ones which sit at local minima, well, the expectation values of all physical constants in string theory are given by expectation values of scalar fields. And if these sit at minima, then this would explain why the constants are truly constant. Because in string theory, this is not clear. Why do we observe physical constants to be truly constant in our universe? They could, in principle, be evolving because they are given by the expectation values of scalars. So it seems that this criterion could have interesting consequences, which would make the no boundary proposal compatible with observations. One can do the same thing that I did before. Now for the ADS calculation, again, look at the domain that are allowable and not allowable. And again, the interesting thing is that also here, the saddle points, which are actually Euclidean anti-de Sitter space saddle points, nevertheless, they sit at the edge of the allowable domain. So it's very interesting that this edge of the allowable domain includes not only Minkowski spacetimes, it also includes the Sitter space and, the Sitter space with no boundary conditions, and it includes Euclidean anti-de Sitter space in the appropriate setting. So all of the interesting saddle points that we've looked at so far seem to lie at the edge of this domain. And yes, so I think this shows that really there seems to be something relevant to this Kontsevich-Segal criterion because it singles out the saddle points. They suddenly are at a special point in the domain of allowable metrics. And it kind of means that it supports this idea that even though you define the theory by looking at metrics which are fully complex, you can flow to to the boundary of this domain, and that's where the physically relevant spacetimes are. Now, one interesting consequence is that it forces you to take only partial steepest descent contours as integration contours, but these have the funny property that they kind of give a compromise between Euclidean and Lorentzian quantum gravity. And yes, I think this is just the beginning. These are the very first steps in exploring what this criterion really means, and much remains to be explored. So thank you for your attention.
Thank you very much. Yeah. So any questions, comments? There are quite a few during the lecture itself. So if there is any further comment, please go ahead, ask and unmute yourself.
I have a small question.
Please go ahead.
So yeah, it was a very nice talk. Thank you. So could you please tell, I probably missed the point. So why can't the fields in the Kontsevich-Segal proposal be complex or complex in general?
They simply assume this.
If I assume some of them to be complex, etc., I suppose the condition on the sum of arguments of lambda mu will go away basically, or be modified.
If the gauge fields themselves would also be complex, then the criterion would be modified. That's right.
And that might have interesting consequences. I mean, either making the constraint go away or put more constraints. Right?
Yes, there are some. So in Witten's paper, he points out that there are sort of there are global conditions also on the gauge fields. So you can have certain invariants which are topological conditions on the gauge fields, which kind of require that an full integral of the space-time of the gauge fields should give a real number.
I see.
But it's not clear what this implies for the Kontsevich-Segal criterion, because that's a local point-wise criterion. Now, what I was pointing out is that if you look at compactifications, then you get potentials in the lower dimensional theory, which really, if you want that theory to make sense, that those things should be real. But then that means that the larger metric, if you include some of the internal dimensions, should include fields which then are forced to be real.
Yeah.
And so it means that there's it gives kind of a consistency condition between metrics in different dimensions. I think this is only a partial explanation, because it does not explain why the gauge field in the lower dimension has to be real.
That's right.
So that's why I'm saying this is not a full explanation. This is an explanation of only some aspects.
Yes.
And well, so I think this is an issue which is not completely clarified yet.
Yeah, because I mean, when you say p-form fields, etc., the natural tendency for me would be to connect it to something like higher spin gauge fields. So,
right.
So, and there, this kind of complications might come up.
Yes. So now.
Ask the question. Yeah.
I can only say what the Kontsevich and Segal, they take this as essentially as the starting point, that all fields except the metric are considered to be real.
Yeah.
And I think to some extent the question, so whether this criterion is valid or not is an open question, right? The way I see this is that I take this criterion as given, and then try to look at the consequences also to see whether this criterion has interesting consequences or not. And
Absolutely.
then what it seems to, what I've just been presenting is that it seems to have interesting consequences, like this fact that the saddle points lie on the boundary of this inequality.
Yeah.
And I would say that gives support that there is something interesting about this condition, but it does not. But I don't think that the condition itself is fully understood from first principles, because it is not, as I said, it is also, to me, it is not completely clear why one should take the scalar fields and gauge fields to be restricted to be real.
Yeah.
Thank you very much, Professor Roy. Are there any?
May I ask a question, please?
Yes, please go ahead.
Now, very nice talk, Jean-Luc, although I have to study a lot to understand what you said. But following up on Kaushik's question is the statement that what prevents you from generalizing to fermions? There, the integrations are much easier because you use the Berezin rules. But then the complexity question becomes more important, doesn't it?
Yeah, I think it should be done. I don't think that anything prevents anybody from generalizing to including fermions.
Mm-hmm.
I think it should be done.
And the other question I had is more sort of philosophical. What exactly do you mean by this compromise in physical terms, in observable terms, of the compromise between Euclidean and Lorentzian? I mean, I see the argument from the point of view of the saddle points and the integration paths. But physically, what are you saying? I mean, what kind of space-times did we have in the beginning? I mean, what sort of compromise, please?
Well, I mean, all I mean is that so it would seem natural from the current physics point of view to just sum over real Lorentzian metrics, mm-hmm. because we know that we have time. All of our experiments are. Show us that our universe has a time direction and three spatial directions, and so it would seem that the natural thing to do would be to sum over Lorentzian metrics.
Right.
However, you immediately face the problem that is not a convergent integral.
Correct.
But only a conditionally convergent integral. So it's not. So that simply, it just as it stands, it doesn't work.
Mm-hmm.
Then. Partially for that reason, or maybe to a large extent because of that reason, partially for that reason, but also for other reasons that have to do, I'll come back in a second. Hawking and Gibbons and other people in the 80s suggested that one should sum over Euclidean metrics.
Right.
Because
right.
Euclidean metrics were seen to more naturally avoid singularities. That's the other thing. If you sum over Lorentzian metrics, because of the singularity theorems of Hawking and Penrose, you necessarily have curvature singularities in these metrics.
Right.
And then the integral breaks down mathematically.
Right.
Whereas if you take the Euclidean Schwarzschild solution, mm-hmm. it's non-singular. And if you take the Euclidean de Sitter solution, it's non-singular, it's a sphere.
Right. Quite
and so then the idea was maybe we should sum over Euclidean metrics, and then this will make the integrals well-defined.
Correct.
But that didn't work either.
It didn't work either, exactly.
Yes, because the integral turns out to be divergent. Even though individual metrics are fine, the integral itself is divergent.
Mm-hmm.
And so I think that's why I was saying here, now there is a kind of a compromise, because you go from approximately Euclidean to approximately Lorentzian.
Right.
And this seems to give convergent integrals.
I have absolutely no issue with that. I'm just trying to see geometrically, what does that mean?
Well, you are actually summing over complex metrics. That's why I think this question is important, of trying to understand which complex metrics should be allowed there. And then this Kontsevich-Segal approach is nice because it kind of says that that there should be some kind of a flow between the complex metrics and then the edge of the allowable metrics.
That's right. That's right.
And so it gives a way of defining quantum field theories in a complex space-time, and by sort of using the analogy with Euclidean quantum field theory, but then it gives you a way of going to the physically relevant Lorentzian metrics on the boundary.
But I was just thinking that is there a restriction on the boundary, on the final boundary? I mean, could you choose a boundary which is sort of close to the compromise region, I mean, where you go from one to the other?
Well, it's not clear in general what the full shape of the boundary is.
Right.
So the boundary contains not just Lorentzian metrics, but also, for instance, these no boundary metrics, and it contains much more than just Lorentzian metrics. And an interesting question is what is this boundary in general? And I think this is simply not known.
Okay. Okay. Great.
Thank you very much, Professor Majumdar.
Yes.
There is a hand by Arif. Maybe we can take the question from Arif Mohad and then Sandeep.
Okay, sure.
Yeah.
Hi. Just wondering if there is any connection with any energy condition.
I think, well,
I mean,
there is. I mean, Matt Visser had a paper following Witten's paper on this Kontsevich-Segal criterion.
Yeah, my question is based upon that.
He pointed out that sort of if you have a metric that is allowable, he pointed out that basically a connection between this criterion and the weak energy condition. But I think that this is not a one-to-one correspondence. So it's not an if and only if statement. So basically it shows that, you know, certain metrics, if already the metric is allowable, it satisfies certain conditions, but it does not mean that all metrics that are allowable must satisfy an energy condition. Basically, it is not. So it is a heuristic way. Yes, in a heuristic way, there is a connection, but it is not completely clear.
And secondly, what one gets is a classical condition, not any quantum condition.
Yes, I think also that the trouble about the energy conditions is that if you are going deep into this into these complex metrics, more towards the Euclidean ones, you see there is no light cone anymore, and there is no and if there is no time direction, you don't know exactly what the energy should be, right? And then it's not basically, so there cannot be a full so I think there cannot be a full correspondence between energy conditions and this allowability criterion.
All right, thanks.
Thank you very much, Arif. Now, Sandeep Panda, please go ahead with your question.
Yeah. So what about zero action? I think, are they ruled out by this criteria? It seems so, right? If the action is...
No, I don't think so. For instance, ordinary Minkowski space would have zero action. Okay, but it would be right at the edge of the allowable domain. I don't see why there is any restriction on the value of the action. Is being recorded. Why? I mean, do you have a more precise? Do you have an example in mind?
Yes, I had the flat example in mind, but point is, at this point, I don't remember what are the zero action configurations other than the flat cases. But then these are, I mean, there are such interesting cases many times occurring. Maybe offhand I can't remember, but I was wondering, because you see the equality seems to be 1, right, for the exponent for zero action, but that is ruled out by Ks. They say less than 1, and then the integral.
So it's at the boundary, right? It is at the boundary then.
So what about this boundary? Are they ruling it out? It's not very clear, right, from their.
No, well, the boundary plays this important role that, you know, that we seem to live on that boundary.
Right.
So this is, in a sense, their generalization of the Wick rotation, or of the, you see, or you can think of this a bit also in the same way as the I epsilon prescription in quantum theory, in quantum field theory. you see, you need this I epsilon, and this epsilon needs to be non-zero. And if epsilon goes to 0, that would be, again, like being on the boundary.
Right.
So it should be thought of, this boundary should be thought of as I think it should be thought of as a limit. And then basically it is the limit of the allowable domain. And that's exactly where the interesting solutions seem to lie.
Right. And another point seems to be that you are not integrating over complex metrics, right? So first you do the Gaussian integration probably over the scale factor, or rather I should say cube your.
Yes.
Yeah.
This includes all possible fluctuations. This is a Gaussian integral, which actually includes all possible fluctuations.
But they can be complex in general, is it? Because in the usual path integral, we don't really think of complex deviations, right? For instance, the free particle Feynman integral. So there you break it up into slices and you just do it over real deviations. So what is it happening when you do the A integration before going to the N integration?
Here it is
I think it's real only, the Q integration.
Q can be complex, that's the thing. So it depends on the boundary conditions, and it depends on, so it's more interlinked with the lapse integral, because one can choose a gauge in which the lapse is constant when you do the integral over Q. But the integral over Q, the way to do it is to split up Q into a solution of the classical equations of motion plus an arbitrary fluctuation. And, and this solution of the classical equations of motion can be a complex solution. And in fact, it will involve n, and n can take complex values.
Okay, yeah.
In general, it is a complex metric.
Right.
And then you add an arbitrary fluctuation. And that fluctuation integral is a Gaussian integral.
Okay, yeah.
But it is a Gaussian around a potentially complex solution. And then you sum afterwards, you sum over all values of the lapse, meaning you sum over all kinds of metrics which are actually complex.
Right. Yeah, it makes sense. But then, since I don't know this, let me ask this anyway. So suppose you do the free particle Feynman integral, okay? And if you allow the complex paths there in the coordinate space, what happens? Does the result change? Because we assume only real paths there. And what happens to the probability interpretation there based on the kernel, whatever you have there?
I'm not sure. Off the top of my head, I cannot say. I would have to look at it. I'm not sure. You see here, though, we are not complexifying the coordinates. We're complexifying the fields.
That's true. Yeah, that is understood. But point is the analog of the position coordinate Q there is the A and N here. So
yeah. So you should
not
think
clear
of it
to
as
me
a,
what happens.
as a complex metric, as a complex metric on a real four-dimensional space-time or manifold, let's say. You know, it's not that the manifold itself becomes now complex dimensional. The manifold remains four-dimensional in a real dimensional, but the metric on it is complex.
Yeah.
Sorry, I got disconnected for a while, but thank you, Jean, for your answer. Yeah, I think it has to be thought about. No simple answers. Yeah, thanks.
You're welcome. Thank you.
Yeah, thank you very much. And any other question?
Yeah, may I ask a question?
Yeah,
sure.
Please.
Yeah, so this is about this not complexifying the coordinates. So, so you basically, so when you take a matrix, this you don't assume a complex structure on the manifold. Only the tangent bundle is complexified. Do I understand this correctly?
Yes, it's not. So it's not that the manifold itself is a complex manifold. That's right.
A complex structure, but I can still have a complex matrix.
Yes, that's right.
Just by complexifying the tangent bundle only. And about this, related to this question of Sudipta, do I understand this correctly? Say, if I say that in the Kontsevich Segal this calculation, they are saying that the path integral can be convergent even if the action has some kind of a complex part. The convergence is affected, although classically this probably will not make sense if I thought in terms of energy, etc. So is that a right understanding, or I'm missing something?
So if the metric is complex, then the action will be complex, and so
it doesn't matter as long as it converges.
So e to the is will be now both contain a real part and a complex part. It will not be a pure phase.
Yeah.
And the amplitude, if you want this to be convergent integral, then you want the amplitude along the integration contours to be get smaller and smaller.
Yeah.
Right, and that's where this criterion comes from saying you want the amplitude to be smaller than 1.
Part and an integral may not matter in the absolute convergence.
Sorry, could you say that again, please?
And also, so this path integral is an integral, and an oscillatory part may not matter because we're looking at absolute convergence. They have a mod.
Yes, if the amplitude goes to 0, then if it is multiplied by an oscillating part, that doesn't matter. That's right.
That's usual stationary phase approximation.
Then you would do either a stationary phase or steepest descent. This is really all the same.
Right.
Okay. Thank you very much, Professor Roy. And thanks to all the participants, and of course, thanks to Professor Lehners for such an interesting and informative talk. I think this will come to an end now, and we'll again resume with some other talk at a later date. So thank you all. Thank you, Professor Lehners.
Thank you.
Thank you very much. Thank you for your interest.
So we are concluding the program now. Thank you.
Okay, thanks very much.
Bye.
Bye-bye.